All right. So in the interest of time, I suggest we get started. So we left off at looking at various types of data that you can use in your project. Tom already mentioned RDFA yesterday, which is W3C recommendation. I'll just flash a few slides to remind you what is it about. It's been the latest recommendation, RDFA 1.1, has been a standard since June last year. And we've already seen some examples yesterday. RDFA essentially adds some new attributes to HTML, right? So these are new attributes you add to your HTML tags. For example, in this case, to say that this is a movie and it has a title and so on, and it has an image representing that movie. Most simple example of annotating links, right? So the one that Tom also mentioned, linking to the license of the page, right? And then you might want to set the subject of your triples, right? So if your triples are not about the page itself, but something else that is described in the page, a topic of the page, if you will, then you want to set the subject using the about attribute. So this is one of the additional attributes that RDFA adds to the HTML language. Okay? And then here's a more complex example, right? So if you define an object, minimally, you probably want to give it an identifier using about. You want to give it a type using typeof, and then you describe the attributes and relationships of that object inside the HTML using rel and using property. Sure. Rel is an existing HTML attribute. Property is something that RDFA adds to the HTML language. Okay. One particular format that you will find out on the web uses RDFA, and it's called Facebook Open Graph Protocol. I like to say that it's a great name because it's three things that it's not. It's not open, it's not a graph, and it's not a protocol. But other than that, it's a well-chosen name for this project. What it does is that, or the way it works rather, is that whenever you click a like button on a page on the web, what Facebook does is that it fetches that page, right? So it downloads that page, and it tries to look for markup in that page, their own markup, which is called Open Graph Protocol, right? This is a format that is based on RDFA. It helps Facebook to understand what the page is about, right? It's important in that sense. So they know that you liked not just the page, but you liked a particular movie, right? For example, in this case, someone clicked on the like button on the movie Rock on IMDb. IMDb pages contain this encoding, right? And whenever Facebook fetches the page, it finds this HTML markup inside the page and knows that it's a movie, right? So it can add it to your personal profile. It can use it to enrich your news feed, right? And so on. And again, the example is the one I showed at the beginning. This is RDFA at a very limited version, right? So essentially they instruct everyone to use RDFA only in the header, right? So they prefer that you put all your markup in HTML head, which unfortunately also limits what you can do, for the simple reason that in HTML head you're not allowed to nest tags, right? So it's somewhat limited of what you can say, but you can say that this is this thing, it has a name, it has a type, and for example, it has an image, right? So these kind of simple things you can express, and the format is RDFA, right? The syntax is RDFA. Let's put it that way. Facebook gives you the vocabulary, right? So it gives you the names of the properties, the names of the attributes. Right? Microdata is, let's say, an alternative to RDFA when it comes to encoding data in HTML. It's been designed as part of sort of the HTML5 process, which has been dragging for years, and microdata is sort of dragging along. It was meant to be a simple way of putting markup in HTML that is more standardized than microformats, right? So as easy as microformats, but hopefully a bit more well specified. HTML5. This is just a reminder to myself as well to note that HTML5 itself is more semantic in the sense that you have tags for things like time and video and article, right? So in a way, HTML5 already has some kind of concepts of the types of entities that are in the page. It is very primitive, and they don't want, of course, to extend the language in this direction. They don't want to have a tag for person, a tag for book, a tag for recipe, a tag for I don't know what. But they have some tags, right, that have some kind of semantic meaning, if you will. All right, here's an example using another vocabulary which I'll introduce later. This is called the schema.org vocabulary. And this is an IMDb page. If you click View Source, you will see that there is plenty of microdata in here. This one marks up the name of the movie. This one, the duration, and it of course contains the duration in a standard format. Sorry, this third one, which is the XML schema format for durations, which is this very strange PT143M, which just means that this movie is 143 minutes long. That's unfortunately the standard way of writing down 143 minutes. And the genre of the movie when it was published. So again, different from what is displayed to the user. What is actually encoded in the attribute value is something that a machine can process. So it's an XSD date format. All right. So how do you collect all this data? Well, linked data, you have to do crawling, right? So I already told you that you can crawl these data sets, you can jump from one data set to the other. So in that case, two things that you need to essentially add to any standard crawler. One is content negotiation. I think Tom didn't talk about this, but the way, you mentioned the concept. Okay, good. So the way that this works is that if your page, like Tom's well-configured homepage, I'm sure there's both an HTML version and sort of a machine-readable version of the same data. Right? So there's an HTML and, for example, an RDF XML version of the same data. Then the crawler needs to indicate that, yes, I want the machine-readable and not the HTML version. So that's called content negotiation. As well as parsing, the myriad syntaxes of RDF. Right? So we mentioned yesterday all of the syntaxes, or at least a good set of them, and we need to be able to parse all of them. Embedded metadata, then we are crawling HTML. The only difference is that as we crawl, we extract data. There's a very useful library called NE23 that you can use there, which tries to parse out RDFA, microdata, microformats, all the different ways data is encoded in HTML. It's an Apache project. With Sparkle endpoints, the difficulty is discovering them in the first place. Tom referred to this. It is a problem that you don't even know where they are, right? So these are like databases sitting on the web. And you can, yes, if you know their address, you can send a query there, except you don't know what the address is, and you don't know what queries to send, right? So you don't know what they contain. Some of these problems are alleviated by semantic sitemaps, void descriptions. These are sort of additional descriptor documents that try to indicate to you what's in a data dump or what's in a Sparkle endpoint. So I'll not show examples of that, but if you're interested, you can look at that. All right. So here's sort of the current state. So we have data dumps and we have repositories of varying quality. If you're looking for data sets, linkdata.org or datahub.io might be a starting point, right? These are essentially the Yahoo directories of data, right? So they try to create a manually curated collection of current data sets. And the linked data cloud, of course, you can try crawling, and some other people have done the crawling for you and made it available. So there's something called the LOD cache, LOD cache. That's a service maintained by a company called OpenLink that gives you a large chunk of this data, gives you API access to a large chunk of this data. There's a search engine called CindyChan, which again is crawling a lot and gives you API access to the data. In terms of how much data is really out there, we have some statistics in a paper that you can look up later, which says that about 1/3 probably by now of web pages have some kind of data, probably around 10% schema.org data. the rest microformats, Facebook's OGP that are popular. There's an important collection mentioned yesterday, the Web Data Commons collection, which is an extraction of data from a publicly available crawl, which is called Common Crawl. And the data itself is available on Amazon. We at Yahoo have built a service which gives you API access to this data, right? So not just the data dump, but have some kind of API access, programmatic access. All right, so you collected a bunch of data. You need to put it together, right? So this is the problem of data fusion. It's often referred to in databases. You have to do the conversion between these various syntaxes, right? There are tools for conversion from non-RDF formats. As we discussed yesterday, there's plenty of Excel sheets out there, and there are plenty of CSV files out there, and there are tools for converting them to RDF, right? There is a huge literature on that. There's also some standardization work on relational databases to RDF mappings. So this is called RDB to RDF, and the languages that you can do, that you can use to map from relational databases to something like RDF. And then essentially data fusion traditionally in the database literature consists of 3 steps. You need to do the schema matching, right? So the schema of the data that you found somewhere may be different from your own schema or someone else's schema, so you need to reconcile them, right? In one data set, it might be called person. In another data set, it might be called people, right? And you have to know that those are the same things. This is a problem that is fairly well studied in the semantic web literature, in the sense that people are trying to create automated tools for ontology matching. There's a competition around this. It's called the OAEI evaluation, Ontology Alignment Evaluation Initiative, I believe, is the abbreviation. And if you look at the website ontologymatching.org, you can find information about this. The bigger problem, or at least as big, is the entity matching problem we discussed in the previous session. And here, again, there are plenty of tools out there. I didn't put particular links here, but if you're interested, I can point you to tools that you can use to do entity linking. Most of this relies on machine learning, so someone actually creating examples, right? So these 2 things are the same, these 2 things are not the same, and then you do some machine learning, you learn on this data, right? You learn some kind of function that is able to discriminate between matches and non-matches. And the last step is blending. So now you identify things that are the same. In RDF, in OWL, which is the language for ontologies, you can express that 2 things are the same thing. So that's one step you can do. You can introduce a new link between 2 things, saying that this one is the same as that one. But you can also physically combine data. So you can say, now we know these 2 things are the same, we want to put them together. Now, as soon as you want to put them together, you might run into the problem that there might be conflicting information, right? So this source says that the age of Britney Spears is 42. This one says that it's 38. Now, what do you do, right? So this is the blending problem. And I would say in semantic search, you probably want to do or can do something more with the data. And that bit more is inference, right? So now you have some kind of logical formalism in which the schema of the data is represented, and you can use that to infer new information. I'll show you an example of that. You might also want to remove data. This might sound strange, but from a retrieval perspective, more data is not always better, right? There is certainly data that is too trivial or confusing that you will never use and that you want to throw away. Because if you don't throw it away, things will match, right? So it will match certain queries that you don't want it to match because you never even planned to use that data. And in that case, you want to remove data. Strange as it sounds. But sometimes your system performance goes up if you do this well. All right. A word about data quality. So, garbage in, garbage out, that applies to any information system. And it's important for a search engine that serves end users, right? That we don't want to serve garbage, right? So quality, freshness, these are important considerations. Especially when you're talking about data on the web. So of course you have no guarantees, right? You just downloaded a data set from somewhere else, right? How do you know that it's reliable, it's good quality? Some data sets like Freebase have some kind of reputation attached to that, but that is not a measurable quantity, right? So you don't know really how many people have been using that data, what was their opinions, and so on. Often mistakes come from the extraction phase, right? So you did some extraction from text, plenty of issues in terms of recognition. You've seen some DBpedia mistakes that come from information extraction. And you want to do some data validation, right, to mitigate this risk. If you want to do something automated, well, you again can build some model of what good data looks like and compare your incoming data to that, right? So, for example, you have people and their heights, and you have a distribution from a known good data collection. The data set is good, so you know what the distribution of the heights in the population should look like. Now you have a model of that distribution, and if something looks different from that in an incoming data set, then probably the data set is low quality, right? You might have an ontology which might contain constraints that are useful for validation. So for example, in OWL, you can say that height must be a number between 100 and 300, right? So if you have a person and whose height is 400 centimeters, that's very suspicious, right? So you might want to take a closer look at that. And then you might want to do this either by experts, or you might want to use crowdsourcing. You might want to have your users involved, right? So users actually ticking things that are suspicious. If you notice in Google, Bing, Knowledge Graph, right, there's always a feedback button. Give us feedback. Tell us that this is wrong, and that's because there are things that are wrong, right? All right. About indexing. So you collected a bunch of data. You want to index it. Why do you want to index it? Well, to speed up everything that comes after, right? If you had infinite amount of time, you wouldn't need indexing, because you could just go through every document for every query, right, and try to see if there is a match. That is not feasible, so you need to pre-index things, essentially create secondary data structures that will help you to look up things quickly. Sometimes you want indexless retrieval. So there are some systems that work without indices. For example, there are some works in semantic web that do online query answering, in the sense that they actually answer queries while crawling the data, or while interrogating remote Sparkle endpoints, right? So in that case, you don't even have the data, you didn't download it, right? You're answering queries as you go along. So in that case, you don't build an index, you don't even have the data, right? You're just answering queries as you go along. That's an interesting case of indexless retrieval. And then the type of indexing is really different in database and information retrieval, and there are good ideas in both. So database style indexing is done traditionally in what we call triple stores. So these are RDF databases, databases for managing RDF data. They are designed for efficient storage and indexing, as well as Sparkle query answering, right? So here, since we want to answer Sparkle queries, we're going to index the data in a way that we can do that efficiently. There are different physical layouts. I'm not going to go into more detail, but how do you lay this out? How do you actually lay out the data in disk or in memory is of course a research question here, as well as how do you do query resolution, right? So you had the Sparkle query, like the complex DBpedia query that I've shown you. How do you process that, right? In which order do you process the joins is the key question. That is the key question in all of databases, and that's important here as well. But there are multiple triple stores. There has been heavy investment in this in the last 10 years, I would say. And there are a number of commercial ones: Oracle, Virtuoso, Owlim, Stardog, Allegro Graph. These are actually all commercial triple stores that vendors actively sell and support. There are some open source ones that have been either released in open source because the company that used them didn't need it anymore, but you find also that some of them are open source and then you have to pay to use it commercially, right? So that's also happens. And there are also what we call graph databases, which are different only in that they have a slightly different data model, right? So they not necessarily strictly inherit or adhere to the RDF data structures, but they have what they call a property graph data model, which is very, very similar with slight differences. But essentially, these stores can be made to look like RDF stores, right? So they can be made to store RDF data and also answer Sparkle queries. So Neo4j would be an example here. And IR-style indexing is something that Roy introduced yesterday. So here the focus is on efficient retrieval of text, of documents. The only question here is, what is a document in this case, right? If you have data, for example, what should constitute a document? Is it really a single value? Is it a triple, right? Is it a subgraph, right? So we're going to chunk up, the graph some way, and we're going to index each subgraph separately so that we can retrieve them separately. Or a resource, right? Is it going to be one particular entity and all the data related to that entity? And then the question is how far we go in the graph, right? So we index just the immediate attributes of this entity, or we index the attributes of related entities as well, right? So that's the question. How do we chunk up our data? That's the question. Really, the differences to text retrieval, as you can imagine, is that the data is structured. So we can have this dilemma, right? How to splice up the data. The other difference is that we understand some of this data. We know that some things have a special significance. For example, labels, right? So labels are more important than some other text, right? The name of the entity is more important than some other text related to that entity. Or the type, right? The type of the entity is clearly very, very important. So we might want to create separate indices for these, right? Or in the ranking phase, we might want to attach a higher weight to matches in these fields. Data types, right? So we are aware that duration is not just a piece of text. It's a duration or a date, right? It's not just a sequence of numbers. It is something we can sort on. It is something we can index differently. Right? But really, the most basic operation we need in all kinds of cases is matching in nodes in the graph, right? Or at least finding out which nodes might be relevant to a piece of text. I'll go very quickly over this because I would really like to talk about more interesting things. But essentially, you have two ways of chopping up your index. One is what we call a horizontal index. In this case, you essentially have two fields, and these two fields are aligned in a way. In one field, you have the tokens in the text here, right? The tokens in the data, right? In the other field, you store for which predicate was this, in which predicate's value did this token appear, right? So this is aligned along positions, right? So the same position in different fields, in different indices, you find related information, right? Okay. And the vertical indexing, as you might have imagined, is sort of the 90-degree rotation of this, right? So we have a separate field for every predicate, and we store the values for those fields. And here, there's no significance between the alignment, right? But only the fields, right, that contain the information. And again, not something I want to tackle in great detail, but these days you want to do this in a distributed fashion using MapReduce. MapReduce was originally invented at Google to do indexing, so it's not surprising that it's good for indexing, right? And we released a tool called Glimmer, which you can use for distributed indexing of RDF data using Hadoop. Ontologies, again, just very briefly, this is a large topic in the semantic web literature. These are the conceptual models that we use in the semantic web. These are representations of a particular domain. For example, you might have something like a friend of a friend ontology, which is an ontology about people. So it will tell you things like that there are people in the world, and there's a knows relationship between them, so a person can know another person, and the relationship is called knows. Ontologies, as they are discussed in the semantic web, they are grounded in formal logic, some kind of derivation of first-order logic, typically. And there are standards. So OWL is a standard that uses primarily description logics. And the rule interchange format, RIF, is a representation of rules, if you will, and they have different layerings of different types of logic that you can apply to these rules. There are various tools that you can use to manipulate ontologies, primarily editors and reasoning engines. There's a very good one, Protege, which is free, but there are also commercial ones in terms of editor tools, editors, and reasoning engines. There are multiple. There are multiple that you can use for free. I'll just give you an example of what reasoning might look like. Well, it might be very simple taxonomical reasoning, such as if something is a subclass of something else, then if A is of the subclass, then A is also of the superclass, right? It might be useful for just checking domains and ranges of relations. For example, you're doing some information extraction. You're looking for a particular relation. Let's say you're looking for companies that acquire other companies, right? Now you extracted a relation between Bill Gates acquiring a company. Now that might be an error because you were looking for companies trying to acquire companies, so you want to throw that away because you know that Bill Gates is a person. Now the ontology might tell you that acquires a relationship between company and company, so it doesn't apply to this particular case, right? But you can do fairly complex reasoning. Much more complex. These are much more complex representations than the kind of UML style representations that are used in software engineering that you might learn in a software engineering course or software development course. The constructs are binary constructs among classes, intersections, unions, negations, and arbitrary Boolean expressions of these, right? So you might have, for example, an ontology about a university, and you might have a very complex subclass relationship, which is not just a subclass relationship between two named classes, but two unnamed classes, right? So everything that teaches a course is a subclass of things that are not undergraduates or professors, right? So this is not something that you can write down in Java, but this is definitely something you can write down in OWL. And then you can do reasoning on this, right? So now you have a data set which says that there's a teaches relationship between John and CS415. CS415 is a course, and John is an undergraduate. Now it follows by reasoning that John must be a professor, right? So John teaches a course, so it's the subclass, it's a member of this subclass. John is not is an undergraduate, right? So John must be a professor, right? Because it's a union, so one of them must be true, right? So these are the kind of things that you can do. It's all fun stuff. So I recommend you play with it. All right, an example of an ontology, though not a fairly formal one, certainly not as formal one as this one, is the schema.org ontology that we already mentioned a couple of times. This is something that was created by the search engines coming together and starting to agree, right? Previously, they haven't, right? Or certainly there were multiple different attempts by the different parties to define schemas. That caused a lot of problems for everyone, right? So this was clearly one of the cases where we started talking to our partners to make sure that we can advance the field, right? We don't get stuck in a way, unnecessarily competing on things that really should be shared and should be used uniformly across the web. The previous example was sitemaps, right? So Tom is correct in mentioning that. That sitemaps is another example, and schema.org is the current example of this type of collaborative spirit, I hope. The way you can imagine this is that people from the different organizations come together and essentially try to work out, for example, what's the representation of a person, what's the representation of a recipe, what are the attributes, what are the values, and so on. And the result is something like this. So you can go to the website schema.org, and you can see that the local business, for example, this class, inherits from the class organization, and that inherits from the class thing, and it has attributes inherited from actually multiple places, and what are their allowed value types. We really have now seen a couple of ways that users might construct queries. So just very quickly to recap them. We're going to use this example. The example information need is that someone is looking for a friend of Alice, and this friend has shared an apartment with her, being Alice, in Berlin, and knows someone working at KIT. KIT is an institute in Germany. It's the Cultural Institute of Technology. So this is what we're going to look for, right? Now what we can do is, of course, we can write down some keywords, right? So that's very easy. Now what the user would do is think of the most important thing in this query. I already mentioned that users have definitely learned to chop down their information needs to just a couple of words. So something like shared apartment Berlin Alice. Is this a complete representation of the query? No, certainly not, right? The user is taking a leap of faith and hoping that this will return something. Okay? But it definitely does not capture the original intent. Or the user might give this original question, in which case you have a case of question answering, right? As opposed to query answering. The user might give a Sparkle query. Again, as I said, unlikely that any end user will ever learn this formalism. But if we would have an expert user, then the user might translate some part of this query into Sparkle and query that way. Or it might be a hybrid, right? So we might have the highly unlikely situation that the user knows both and gives us both, right? I'll tell you, part of my query I translated into a structured format. Part of my query I threw in as keywords, and now give me the best thing that you can do. This situation might come out in cases also in situations where the user doesn't explicitly write this query, but for example constructs it using faceted search, right? That is probably a more likely scenario that the user did an initial search, right? Ended up with some results, and then does some faceted navigation on those results, right? And then you would have a combination of structured and unstructured query as well, right? Now, how do we get from unstructured to structured queries? How do we interpret queries? Well, this is the flip side of document processing.